Okay guys, in the previous lecture earlier we studied that how we can interpret our system of linear equations. So there were basically two ways, row view and the column view. Now in this section explains a systematic way to solve a linear equation, and the method is known as elimination. Now in high school we studied how to resolve this system of linear equation. It's a 2 by 2 system. So what we studied was that we basically have to eliminate this entry. Now why do we do that? So to make this system into a upper triangular form, right? So what we do is we basically multiply this equation by 3 and then subtract this equation from the second equation, and the form that I get is the matrices that I get is of upper triangular form. So we then solve it by back substitution. The method is known as back substitution, where because we solve it from bottom upwards. We first go to the bottommost equation, find out the value of the variable, and then start putting it in the above equation. So if I find out the value of y from here and then substitute it here to find out the value of x, and that is how we resolve this system of linear equation. Now why did I bring this topic, which we have already studied in high school, is to introduce you with the new terms. Okay, that we will be using frequently for our later inferences. The first one is a multiplier. So to understand this, let's look at this system only. First I would have to explain you what is a pivot. So pivot is basically the anchor we use to eliminate the entries below it. So here my anchor is 1, 2, because I have to eliminate my 3 here. Okay, 3x. So I basically 1x is the anchor so that I can eliminate my 3. So my 1 is my pivot. Okay, and the number that I multiplied with, in this case it's 3, right? So this is my multiplier. Okay, so this one was quite easy. So if I look at another system, let's look at this one. So basically this is my entry that I will be using to eliminate this entry, right? So this is my pivot, and the number that I multiply it with, in this case it's 3 by 4. So 3 by 4 is a multiplier. Okay, and now I have acquired my upper triangular form. So that is our main goal of the elimination method. So our pivot is what? Our first non-zero in the row that does the elimination. Now why I have written non-zero here? Because the entry has to be non-zero. So if it were 0, let's assume, so no matter what number that I multiply it with, I can never eliminate this entry, right? So it always has to be non-zero, and it is basically the anchor we use to eliminate the entries below it. So that is my pivot, and that is the formula of the multiplier. You do not have to remember the formula. Okay, so let's look at this system where you basically have to tell me what is a pivot. So in the first row, first non-zero entry, here in this case it's 1. Now let's move to the second row, and first non-zero entry. So first one is 0, so we will move rightwards, and then I got here, so this is my pivot. And for the last row, my last entry is non-zero, that is 1, so that is my pivot. Okay, so uh, now we move towards why when can our elimination method fail. So basically the whole agenda of elimination is to find the solution, right? So if I have no solution or infinitely many solutions, that is when my elimination may fail. So first case is a permanent failure with no solution. Why do I say permanent failure? Because it can't be fixed. So if a system has no solution, this is basically a failure that can't be fixed. So I have taken this system where I do the multiplication elimination and I get here. Now you will realize here that no matter what value of y I put here, this equation can never be satisfied, right? So no value of y can satisfy this equation, so it basically has no solution, right? So if I interpret this using a row picture, okay, so what I do is basically I take these two equations and I plot them. And what in the previous lecture we studied what was the how did we find solution through row picture, is to find the intersection point of the two lines, and these lines are parallel, so they have no intersection. So basically this equation has no solution. So if I look at the column picture as well. If I interpret it with the column picture, how do I do it? I basically first plot my column vectors, like my coefficients of my variables. These are my components of my column vectors. So if I plot them, so what did the column picture say? So you basically have to find the linear combination which would lead to the resultant vector 1 comma 11. Now you here in this system, my 1 comma 3 and my minus 2 comma minus 6 both lie on the same line, and my 1 comma 11 is in a completely different direction. Like if I had to plot my 1 comma 11, it would be somewhere upwards in this line. Okay, so it is in a completely different direction, and no combination of these two can lead me to my point here, because it's basically could span through this line only. So no combination would lead me to 1 comma 11, so it basically has no solution. So we basically have confirmed it through row picture and column picture as well, that my system has no solution. Okay, and the second one is a permanent failure with infinitely many solutions. So if I look at this system, okay, I have now changed my constants from 1 comma 11 to 1 comma 3. So now if I resolve this using elimination, I would get here. Okay, so you would realize here that every value of y satisfies this equation. So y has infinitely this has basically infinitely many solutions, because I can put any value of y here, and for the y there is a corresponding x value that could be computed from the above equation. So this basically system has infinitely many solutions. Now why is it a failure? Because our number of pivots has to be equal to the number of equation. Now why is it so? This is the topic of a rank nullity theorem, so we will study that in a lot more detail. Ki why is that so? Ki the number of equations, the number of pivots has to be equal to the number of equation. That is basically for the unique solution, right? So you would realize here I have my first pivot, but for the second equation I have no pivot because my pivots can't be zero. So that is why our system has failed, and it is a permanent failure with infinitely many solutions. Now this is my 2 by 2 system, right? So for a 3 by 3 system I have taken the matrices form. Now for the what did we study so far is I take my pivot and make the entries below it 0. Okay, so for the 3 by 3 system, it's a what we do, first of all I take my first element and do the row operation to eliminate the entry below it. Now this is the row operation I performed, and now my this entry has become 0. This one is already 0, so I will move to the next row and look for the first non-zero entry. So this one is already 0, so I move towards the second, move rightwards towards the second entry. Now I will use this as my pivot to make the entry below it 0. फिर से uh, I'm just फिर से repeating what I have said so far, so it becomes clearer for the 3 by 3 system as well. Okay, so this is the operation I perform, and now I have gotten my upper triangular form. Okay, this is my upper triangular matrices, because all the entries below the diagonal entries is 0. Okay, so that is my upper triangular form. Okay, so now you are clear with what pivots are and how do we do it for the 3 by 3 system as well. And for the B, you perform the same these operations on the B column to obtain C, to obtain the resultant C. So that is how you do it. To simplify it, you basically have to convert your system, transform your system from Ax equals to B to Ux equals to C for the simplification, uh, for the for resolving the system of a linear equations. Now instead of doing the tedious job of first performing the elementary operations on A and then on B, what we can do is basically augment our matrices. Okay, so what we do is we basically include B as the last column in the A, and then perform elementary operations on them together to get to our resultant augmented matrices. So matrix A is now augmented by the column A, and then we basically perform our elementary operations as we did before to get to our resultant matrices U and C, and this is what we denoted as augmented matrices, and that is how we denoted it. Okay, so yeah, okay. So I have one homework question for you as well. Ki how can we resolve this system? Now this is the third. Actually, this is the third failure in the elimination breakdown. This is the third failure. But I didn't discuss this before. I will be discussing this in the upcoming lecture or the next lecture. So you have to मतलब थोड़ा सा सोच के आना कि how can the system be resolved? Why is it a failure? Because our first entry is 0, so you can't make the entries below it as 0. So it's basically a temporary fail which can be fixed. Okay, so that is your homework question. So now we move towards the elimination matrices. So in this we combine two ideas of elimination and matrices, and the goal is to express all the steps of elimination in the clearest way possible. Okay, so I have taken my so what is basically the goal here is ki the elementary operations, I can perform that with the help of the multiplication of a matrices with the original matrices as well. So instead of doing the elementary row operation manually, what I can do is basically multiply it with some matrices to perform that operation for me. So how do I get that matrices? Okay, so what we do is basically take the identity matrix. Okay, so the operation that I performed on my original matrix, I take that same operation and perform it on I instead of A, and that is how you compute the E matrix. Okay, this is known as elementary matrix or elimination matrix. So I take this operation and instead of performing on A, I perform it on I, and the resultant matrix that I get is my elementary matrix. And I have denoted this one with e to 1 because we basically used it to terminate this entry, right? So this is in the 2, 1 position, so I denoted this matrix with e to 1. So when I multiply it with A, it would do the same operation that my row elementary operation did, and I get my resultant matrix. Okay, so now to convert this into a upper triangular form, I have to eliminate this this entry as well. So for that, what elementary matrix I would require? E32. So if I perform multiply it with this, I would get my upper triangular form. Okay, so in this case I only require two matrices, but it differs from system to system. Okay, so if I denote all of the elementary matrices with E, I would get to this equation. Okay, okay, so if I although we are going to study inverses of the matrices later, but for the time being let's multiply both these equations with E inverse. Okay, you might have studied in high school ki what would this lead me to, like what would be the result of this identity matrix. Okay, and this one becomes E inverse U. So I can denote my E inverse with L as well, and this is known as the LU decomposition. Okay, so basically what we have done here is कि I have decomposed my A into lower triangular matrices and upper triangular matrices. Okay, so L is basically a lower triangular matrices. So my A is decomposed into lower triangular and upper triangular matrices. Okay, so this is known as LU decomposition. This is basically the intro for the next lecture. Okay, now comes the last topic for today, that is how to undo an operation. Like let's assume if I wanted my original matrices back, so, like from here I got to here, but what if I wanted to undo my operation? That's when inverse of elementary matrices come into the picture. So what basically needs to happen is कि when I multiplied it with E, when I multiplied my matrices A with E, it does something to the rows. But if I multiply it with E inverse, it should undo that thing. Okay, so if I did this operation, I would simply add what I subtracted. So this would like the resultant of this is this only, right? So what I basically do is to undo what I basically do to undo this thing is to multiply this, the resultant that I got, with the inverse of my elementary matrix. Like this is my inverse of the elementary matrices that I performed. Okay, so if I multiply it with the resultant, I would get to my original matrices A. Okay, so that is how you undo an operation. Okay, so that's it. Now points to remember are कि a linear system Ax equals to B can be transformed to Ux equals to C after elimination. Okay, the second one is the upper triangular system is solved by back substitution. From bottom upwards, you solve your system of linear equation starting from the bottom. Okay, and when breakdown is permanent, the system has either no solution or infinitely many solution. Okay, so